Imagine for a moment that you're a space explorer, floating in the vastness of the cosmos. As you drift through the inky blackness of space, you spot something in the distance, a region so dark that it seems to devour even the light around it. Your heart races as you realize what you're seeing: a black hole. Curiosity overwhelms you, and you find yourself drawn closer and closer to this cosmic body. But what would actually happen if you took the ultimate plunge and fell into a black hole? Today, we're going to embark on a mind-bending journey to explore this very question. Buckle up, because things are about to get weird. Before we dive headfirst into our hypothetical cosmic adventure, let's take a moment to understand what black holes actually are. The term black hole itself is enough to send shivers down your spine. It conjures images of an all-consuming void, a place where the laws of physics break down and reality itself seems to unravel. But despite their ominous name, black holes are actually fascinating cosmic objects that play a crucial role in shaping our universe. At their core, black holes are incredibly dense regions of space where gravity is so strong that nothing, not even light, can escape once it passes a certain point. How are these cosmic monsters born? Black holes are forged from the remnants of massive stars that have reached the end of their lives. When a star with a mass more than about 3 times that of our Sun exhausts its nuclear fuel, it undergoes a spectacular death. The star's core collapses under its own gravity, triggering a supernova explosion that outshines entire galaxies. What's left behind is a small, incredibly dense core, and if that core is massive enough, it becomes a black hole. But not all black holes are created equal. Astronomers have identified 3 main types. Stellar mass black holes. These are the smallest variety, ranging from about 1 to 100 times the mass of our Sun. They're formed from the collapse of individual massive stars. Supermassive black holes. These cosmic giants can have masses millions or even billions of times that of our Sun. They're thought to lurk at the centers of most galaxies, including our own Milky Way. Intermediate mass black holes. As the name suggests, these fall somewhere between stellar mass and supermassive black holes, with masses between 100 and 100,000 times that of the Sun. They're still somewhat mysterious, with only a few confirmed detections. The anatomy of a black hole. Now that we know how black holes are born, let's take a closer look at their structure. First, there's the event horizon, the point of no return. This is the boundary beyond which nothing can escape the black hole's gravitational pull. If you cross this threshold, you're in for a one-way trip to the center of the black hole. Beyond the event horizon lies the singularity, the heart of the black hole, where our current understanding of physics breaks down. Here, matter is crushed to infinite density in an infinitely small space. It's a place where the laws of general relativity and quantum mechanics collide, creating a puzzle that continues to baffle even the brightest minds in science. Now, let's return to our hypothetical space adventure. As you drift closer to the black hole, you start to notice some strange effects. The immense gravitational pull of the black hole begins to distort your view of the universe around you. Stars behind the black hole appear to bend and warp, their light twisted by the black hole's gravity in a process called gravitational lensing. It's as if you're looking through a giant cosmic magnifying glass, with the black hole at its center. As you move even closer, you notice another bizarre effect. Time itself begins to slow down relative to the rest of the universe. This phenomenon, known as time dilation, is a direct consequence of Einstein's theory of general relativity. The closer you get to a massive object like a black hole, the slower time passes for you compared to an observer far away. As you approach the event horizon, you face a moment of truth. Once you cross this boundary, there's no turning back. But here's where things get interesting. From your perspective, nothing particularly dramatic happens as you cross the event horizon. You wouldn't feel a sudden jolt or see a flash of light. In fact, due to the extreme warping of spacetime near a black hole, you might not even realize when you've crossed the point of no return. However, if someone were watching your descent from a safe distance, they would see something very different. As you approach the event horizon, you would appear to slow down more and more, eventually seeming to freeze in place. Any light emitted from your ship would be increasingly redshifted, stretched to longer wavelengths by the intense gravity, until you fade from view entirely. This discrepancy between what you experience and what an outside observer sees is one of the many mind-bending aspects of black hole physics. The spaghettification dilemma. Now that you've crossed the event horizon, your fate depends on the size of the black hole you've chosen for your cosmic dive. If you've picked a smaller stellar mass black hole, you're in for a rather unpleasant experience known as spaghettification. The tidal forces near a stellar mass black hole are so intense that they would stretch you vertically while compressing you horizontally. Imagine being pulled apart like a piece of taffy, stretched into a long, thin strand, hence the term spaghettification. This process would occur long before you reach the singularity, turning you into cosmic spaghetti in a matter of seconds. However, if you've chosen a supermassive black hole for your adventure, like Sagittarius A** at the center of our Milky Way galaxy, you might avoid this grisly fate, at least initially. The tidal forces near the event horizon of a supermassive black hole are much weaker relative to its size, so you could potentially cross the event horizon without being immediately torn apart. Inside the black hole, once inside the black hole, you enter a realm where our understanding of physics begins to break down. The extreme curvature of spacetime inside a black hole leads to some truly bizarre effects. As you fall deeper into the black hole, space and time essentially switch roles. Just as you can't avoid moving forward in time under normal circumstances, inside a black hole, you can't avoid moving toward the center, the singularity. Every path, every possible future, leads inexorably to the center of the black hole. As you approach the singularity at the center of the black hole, you enter a domain where our current theories of physics fail us. The singularity represents a point of infinite density and zero volume, a concept that defies our understanding of the physical world. At the singularity, the curvature of spacetime becomes infinite, and quantum effects likely become dominant. Some theories suggest that the laws of physics, as we know them, simply cease to apply here. You might encounter exotic phenomena like quantum foam, a roiling sea of virtual particles popping in and out of existence. While your journey into a black hole seems like a one-way trip, some theoretical physicists have proposed potential escape routes, although these remain firmly in the realm of speculation. One idea is the concept of a white hole, essentially the opposite of a black hole. While a black hole allows nothing to escape, a white hole would allow nothing to enter, instead spewing out matter and light. Some theories suggest that black holes and white holes might be connected by wormholes, hypothetical tunnels through spacetime that could provide a shortcut to distant parts of the universe. Another speculation is that if you waited long enough inside a black hole, it might eventually turn into a white hole. Due to the extreme time dilation inside a black hole, what might seem like billions of years to an outside observer could feel like just moments to you. However, it's important to note that these ideas remain purely theoretical and are not supported by observational evidence. Recent breakthroughs, even black holes themselves, for most of history, were purely theoretical objects, predicted by Einstein's equations, but impossible to observe directly. However, recent years have seen remarkable breakthroughs in our ability to study these cosmic enigmas. In 2015, scientists made history by detecting gravitational waves for the first time, caused by the collision of two black holes 1.3 billion light-years away. This discovery not only confirmed a key prediction of general relativity, but also opened up a new way of observing the universe. Even more dramatically, in April 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole. The image shows the shadow of a supermassive black hole at the center of the galaxy M87, surrounded by a bright ring of hot gas. This groundbreaking achievement marked a new era in our ability to study these mysterious objects. For now, though, it's probably best to admire black holes from afar. After all, Some journeys are best left to our imagination. And if you enjoyed this cosmic journey, why not join our community of space enthusiasts? Hit that subscribe button to stay up to date with all things astronomy and space science. Don't forget to ring the notification bell too, so you never miss an update.